Yes, good evening, everyone. I'm just waiting for 5 minutes. After that, I will start. If anyone wants to join, they can join, and after that, I will start. So everything is visible and audible. I think everything is visible and audible. Is it? Okay. Just wait for 2, 3 minutes. I will start from 6:05. If anyone face any problem, write in the message section. Okay. Okay, it's already 6:05. So we can now start. Let's check one more time. Okay. Okay. So good evening, everyone. Myself, Amiyo Mandal, and PMRF Scholar at IIT Roorkee. I am working under Professor Peria, and I am doing here my PMRF teaching assistantship duty for a NPTEL course. The name of the NPTEL course is Fundamental and Applications of Dielectric Ceramic. The course instructor is Professor Ashish Garg from IIT Kanpur. And today I am going to discuss about the assignments problems of week 5. Okay, okay. So what you have learned in week 5, you have learned in week 5 losses in dielectric constants. So different types of dielectric losses you have learned in week 5. Frequency dependence of dielectric constant, although you have learned it in previous lectures also, but in more details, what relaxation is, what resonance is, in which resonance relaxation and um, resonance occurs, everything you have learned in this week. And dipolar polarization and its relaxation, how dipolar relaxation works, and then the explanation of dipolar relaxation. The Debye explanation. Debye equation explains the dipolar relaxation process. And at last, impedance spectroscopy. So total 5 lectures you have done in week 5, and you have learned about all those things. And every questions are based in this assignment for week 5 in this on this basis of these lectures. Okay, there are 15 questions I am going to solve and discuss and clear the concept of each of the problems we have learned. Okay, so let's first start question number 1. Okay, if anyone face any problem, please let me know in the message section. I continuously check the message section. Okay, so let us start the question number 1. Okay, the dielectric relaxation. Question number 1. Let's see the question number 1. That dielectric relaxation. One is relaxation is manifested by pitch. So you learned about relaxation and resonance and relaxation, two process, where in the dependency of frequency of dielectric constant. Dielectric constant is of dielectric constant epsilon r star. This is a complex quantity. Complex quantity, okay. And it can be expressed as epsilon r dash. This can also be expressed as kappa star plus I epsilon r double dash. This is the real part and this is the imaginary part. Okay. In these two terms, epsilon r dash and epsilon r double dash, dielectric constant can be expressed. Okay. And you already have learned about the dependency of epsilon r, this dielectric constant, with with frequency omega or f. Okay, this concept will apply here, and we see what where in which region, in which frequency region. There are different frequency regions. Okay, different frequency regions. Different frequency regions. Okay, in this different region, uh, this dielectric constant depends. Its value depends. Okay, so let's start. Uh, you already know about different types of polarization. Okay, different types of polarization. Polarization is expressed as capital P. Okay, so different types of polarization. Polarization can be expressed, in four types, different types. Polarization of electronic polarization, polarization of ions, polarization of ions, polarizations of dipolar polarization, and polarization of interfacial polarization. These four types of polarization, you already have learned about what this polarization tells about and how this polarization generates. But what is the dependency of this polarization with respect to the frequency? Okay, so you can see uh, this graph where epsilon dash means the real part of epsilon, real part of dielectric constant. Real part of dielectric constant varies with log omega, means a logarithm of frequency. This is the frequency variation, and logarithm scale has been taken due to simplicity or due to uh, the presentation simplicity. So, okay. So you can see that different types of polarizations occurs at different regions of frequency. This is the frequency regions. You can see the electronic polarization, ionic polarization, orientational polarization, interfacial polarization exist in a dielectric material. So in which region this electronic polarization occurs, and its variation of real and imaginary part of dielectric constants with respect to the frequency. You can, although seen in general, not in this real imaginary form, means this complex form. Here you will see in complex form that in uh, the frequency range of 10 to the power 15, 10 to the power 15 hertz. Okay. In 10 to the power 15 hertz, there is a resonance of electrons inside the dielectric material. Resonance means at a certain frequency. Okay, at a certain frequency, there is a certain peak, where ions and electrons and their polarizations can be separated. At there is a certain value, there is a certain value, there is also a certain value. Okay, and this value is 1. Okay, greater than of 10 to the power 15. This determines the one value of a dielectric constant, real dielectric constant. But in the case of imaginary cases, we will see later in very explanation, although you have learned in the lecture classes, I just simply show you that, recap you how this happens in this, how the peaks at a certain frequency matches with relaxation and resonance frequency. So in case of ionic and electronic polarization, the resonance frequency, uh, resonance occurs at a certain frequency. Okay, and their corresponding losses. This term of this term is significant for dielectric loss. We will see later. Okay, so resonance in this region, two peaks. This is a region where one resonance occurs, and this is a region where one resonance occurs. And this is the region for orientational polarization, means when we just move away from ionic to dipolar orientation polarization. There we see the relaxation relaxation type behavior. Relaxation type behavior means relaxation in vibration. These two terms, ionic and electronic polarizations, occurs due to which? Due to which factor? This occurs due to the local vibration, means vibration of molecules from its original positions. Simple harmonic motion. But in these dipoles, they orient themselves in the response of electric field, with response of electric field. So it takes times. When it takes times, then there will be certainly a region of frequency. We call it a resonant relaxation frequency. That's why dipoles. That's because dipole has larger mass. There is a mass difference also. Mass of dipoles is larger than dipoles, greater than of ionic and electronic. So mass variation, when mass is larger masses shows higher, takes larger time, and that's why a relaxation occurs in a dipolar cases. So that is why when we move forward from ionic to dipolar region, in a smaller region frequency, then we see the relaxation behavior, and its corresponding losses also can be seen. So here you already have learned everything about that. So I highlighted some very important portion, that if the frequency of the field is very high, 10 to the power 15, greater than 10 to the power 15 hertz. Okay. So no dipole system will able to follow the field oscillation, and in such a situation, no mechanism will follow. And hence, as I already have told that epsilon r value tends to 1 value. Okay. These are some important points. And at a frequency below 10 Hz, the directivity property are affected by the frequency of field. So in case of electronic and ionic polarization, what is the reason? Mechanical oscillators will be a red factor. So the characteristics of any mechanical oscillator is resonance at a certain frequency. Okay. So in the case of bipolar and for orientational polarization means dipolar polarization, what happens? No direct mechanical restoring force. Here, no mechanical forces are there. No restoring force. Mechanical restoring forces are there in the case of dipoles. So what? Dipoles and what the relaxation process in case of dipolar polarization? So when a driving force is present, when we apply some external electric force, okay, there is an equilibrium state with average of net dipole moment. Net dipole moment generates. Okay. If the driving force were to disappear suddenly, then the ensemble of dipole is assumed a new equilibrium state. That is the random distribution of dipoles. This is very important point. When we remove the electric field, external electric field, then this oriented dipole randomly distributes among each other, and this takes some time. This is this is for the relaxation time. That's why no resonance process has been generated in dipole cases, and the relaxation process will generate in case of dipole. And the time taken for this relaxation process is called the relaxation time. So this process is called the resonance process, and the frequency is called the resonance frequency. This is also called Arrhenius type behavior because in these cases, the activation energy type. You already know about the Arrhenius law, that exponential of minus EA by KT type. Okay, the reaction constant is proportional to this type of. Okay, so activation energy generates. This is called the activation energy. Okay, symmetrical body. Yes, when we apply the electric field, we have already learned. I will discuss it later in next questions also. That there is a equilibrium separation in case of from polar molecule. This is a polar molecule like H2O. Okay, so this PVDF, these are called polar molecule. This sometimes polar molecule. They react with the external electric field and changes its positions, and according to them, they are they so during this change of position, uh, uh, they have to step a barrier potential they have to they want to if they want to reach at this position, they have to cross this barrier, and during crossing this barrier, um, uh, energy called the activation energy is required, and that's behavior are told in Arrhenius law. So I am not going to go the details. So Arrhenius is jump, this probability of jump between these two sides. This is side 1, this is side 2. So jumping probability from this side to this side is called, this is related to some more Arrhenius law, and all these are regarding the relaxation process also. Okay, so we can now answer this question that dielectric relaxation is manifested by which. So we can go to the options. Resonance in a dielectric constant at frequencies below that of ionic polarization. Okay. Um, Resonance. Dielectric relaxation may not be a resonance. Okay, so the resonance will not be option. Option B, a step in the dielectric constant at frequency below that of ionic polarization. Okay, ionic polarization below that of ionic polarization means this. So step This option will be correct. Zero dielectric loss, no, there must be a dielectric loss. Epsilon double dot signifies loss constant. So you can see at the relaxation region, there must be a loss. So zero dielectric loss may not be true. And the motion of the charges following Arrhenius type behavior. Okay, I have already discussed about this, and this option will also be correct. Next, we are going to the question number 2, that following graph, a graph is given, uh, and the question telling us about that represents the dependency of polarization on time. Polarization, how polarization depends on time. Okay, how polarization depends on time. We already have uh, seen that it depends on frequency and frequency. So it also dependent must be also dependent to time also. And we have seen that different types of polarizations and their dependency with frequency, and the electronic and ionic polarization, electronic and ionic polarization. Okay, these two depends on very high frequency. Okay, means they needs very low time. They needs very low time, very short time. In a very short time, electronic and ionic polarizations occurs. So here the time clock occurs. Time is increasing. So what very short time decrease? This region, very short time. This one region is lying inside the very short time, 10 to the power minus 15, 10 to the power minus 13. Okay. Second, in this very short time, ionic and electronic polarization occurs. And when time increases, means when the frequency decreases, then in this region, in these two region, what type of polarization occurs? Dipolar polarization will occur and dipolar relaxation will occur. So this region is dipolar polarization region. And after that, a saturation of the polarization exists after um, increment of the time, after greater time. So, and the question is based on this concept. So you can now see that, okay, let's first see that what dipolar relaxation, okay. Okay, so in this region means when time is sufficient time like 10 to the power minus 13, 10 to the power minus 6 to 10 to the power minus 13 second in this region, dipoles are oriented when a sufficient amount of electric field is applied, and after removal of the electric field, dipoles orients randomly to themselves, and in these cases, dipolar relaxation process, the times required to randomly oriented, random orientation is called the relaxation time. So these are the concept. Okay, so let's see it. I have just presenting here. I'm just presenting here what dipolar relaxation is. It's telling about the relaxation process occurring mainly ceramics, ionic solids, especially glass, and this material applies damped oscillation, damped forced oscillator approach. Does not work in low frequency region. Okay. Okay, next, in such cases, the structure of the solid plays an important role because movement of charge may have to occur over many atomic distances and can be classified as diffusional in nature. Okay, so these are some important points. Atomic distances may and can be diffusional in nature. So when distance increases, potential energy of distribution in a glass has been shown that we do not get there must be variation of energy in a minimum distance, certain like a distance. I think Sony you already have learned about this. So what is the main thing here? This graph. Okay. This is an ionic solid. Hmm. The application of field. First, almost instantaneous development of electronic polarization and ionic polarization is a very short time, as I have already told that. First, at a very short time, instantaneous time, electronic polarization and ionic polarization generates. These two types of polarization generates in an ionic solid, followed by slow development. And this is the slow development generation. Slow development of the dipolar polarization. It is the dipolar polarization to a saturation polarization. These are the slow development. Okay. Slowest process. Okay. So this is so from here you have learned things about this. And this is the important expression how polarization, so variation of polarization. Okay. You can see that there is a variation of polarization with time. This is the polarization and this is time. So variation of polarization with time. This factor, this factor depends on which? Depends on saturation polarization and dipolar polarization only, not the electronic and ionic polarization. So, and their difference, okay, their variation, they are not linearly varying. Saturation polarization is biggest, so their difference, Ps minus Pd. Difference between saturation polarization and dipolar polarization is mainly varying. So it must be dependent on Ps minus Pd and its change, that is the relaxation time. Okay. Okay, so this is termed as a, so mainly it depends on it, and this is 1 by tau term. We have to multiply it, and this is called as a proportionality constant. You already have learned about this equation. This is a very important equation in lecture classes you have already learned. I also briefly discuss about this equation and how it generates in uh, bistable lattice in a, for dipolar polarization. Okay, by calculating, there is a huge calculation um, where you see that how dipolar polarization and its saturation polarization varies with time. Okay, so we can now move to the question that so question is which are represented by 1 and 2. This 1 represents electronic and ionic polarization and 2 represents dipolar polarization. Okay. Okay. So next question is question number 3. In terms of migration energy, that is migration energy. Okay. That is migration energy. EA, it's also called the activation energy. Activation energy from Arrhenius law. Activation energy. Migration means from one side to another side, the energy required to just jump away from one side to another side, the required energy, you see here, the required energy is called the activation energy. Okay, I will see in a very clear image. Uh, so that is the concept of migration energy and the temperature. What will the jump probability? Jump probability P temperature. Okay. That is this type of behavior is called the hopping. Hopping. Okay, from one side to the another side. So, and this is mainly based on the bistable model. So bistable means this is one stable position and this is another stable position. When is after the application of electric field. for only for dielectric dipolar relaxation process. That you can see that this is a equilibrium position, and the distance between two equilibrium positions for each side position when uh, dipolar position have to be for jump have to jump from one side to this side, and this requires this much amount of energy. This is called the activation energy. Okay. Here you can see when sodium movement of glass, sodium in a glass, sodium movement of glass. This is a clear, nice example. Okay, of hopping. We consider a bisteral model. Okay, so the probability of jump between side, that is F, probability has been termed as F. So probability of jump between side is depends on exponential factor. Exponential factor. This is exp minus A by KBT. Okay, means F equal to A by exponential of A by KT. Okay, means when temperature increases, what happens? This term decreases, and this term also decreases. Overall, this um, hopping probability decreases, increases. This term decreases means F increases. Okay, so temperature is a very vital factor here. Okay, for hopping probability. But the question is that what is the expression of probability? Expression of hopping probability. This is hopping probability. Hopping probability. Okay. It depends on temperature and depends on activation energy of two uh, nearby sites. Question number 4. Okay. So the ionic and dipolar polarizabilities are derived considering it is not dipolar. The question there is maybe some correction. It should be electron. Okay. So let's see that the ionic and the electronic polarizability, ionic, electron. What polarizability is? Polarizability is nothing but electric field, polarization per unit electric field. Okay, per unit electric field. So ionic and electric polarizabilities are derived considering charge dipoles act. Sorry, it should be dipolar polarization because here we consider actually the simple harmonic motion. Okay. Okay, let's see the frequency dependence of dielectric property, that is resonance. Description of ionic and electronic phenomena. Here we must consider that charge dipoles behaves like linear harmonic oscillator in case of ionic and electronic polarization. This is a very important that's a very important concept that we must consider linear harmonic oscillator as a charge dipoles as a linear harmonic oscillator. Then they also follow the equation of motion. I am not going to deep in the details. And equation of motion tells you have already learned this is a restoring force. This is from the driving for damping force. Okay, damping force. Or here you can see the restriction. Here you can see friction, light force, friction is equals, and this term from oscillation. So in these three terms, the equation of motion, that is force. Okay. So everything for by this is the equation of motion. By solving this equation, we get x value. Okay. So some cases has been tried here. That first case when applied field is DC and is switched off at a given moment. Okay. The restoring force pulls back the charges to the equilibrium and the friction is zero. There will be no damping of oscillation for a DC, and friction is present and the system will have a damped oscillation. Okay. And in these cases, x is represented at this, and xt, after solving this, we will get this value in terms of omega e naught, omega 0 I. Omega 0 I is what? Omega 0 I is the natural frequency of the particle. Okay. And gamma is the frictional coefficient of the species. And x is the displacement from the equilibrium. So these terms are important. And n atom per unit volume gives this. So when we apply n atom, then we will get the polarization concept. So dipole moment will be this. Okay. Q into x. And polarizability. That is the polarizability term, ionic or electronic polarizability. Okay, alpha I. That is alpha I. Alpha I, ionic or electronic polarizability. And ion for ion cases, the reduced mass. This is reduced mass. Okay, this can be expressed as multiplication of cations and ions mass and their corresponding ratio of multiplication and summation. So polarization, just multiply the n value, number of dipoles per unit volume, and dipole moment, you will get the polarization value and the corresponding susceptibility value. Susceptibility is nothing but P equal to Y epsilon naught into E. The susceptibility just E by epsilon naught into E. Epsilon naught into E. Okay. So just divide by epsilon naught and uh, E, you will get the susceptibility value. Okay, it has been divided and E have been cancelled out. So this is the final expression and the corresponding E value. Complex quantity. This is a complex quantity. Okay, complex star value. So from here, you find the relaxation part, imaginary part and real parts of dielectric constant. Okay, real and imaginary parts of dielectric constant. So this is the real part and this is the imaginary part. Okay, all this depends on phase value, omega and omega naught. It varies with omega, function of omega, omega naught. Okay. In cases of here is you also see. So how it will vary in the case of real part of dielectric constant minus 1 from this expression, and from this expression, the imaginary part of dielectric constant, how it varies? It varies like this, and at a certain frequency, there should be a resonance frequency. And this term actually tells about the loss factor. Okay, and loss factor at a certain frequency, it rises up. Okay, so this is mainly so telling about the resonance frequency, how when uh, we do not consider the local field. If we consider the local field, then E value should be this. Okay, so okay. So in these cases, when omega less than omega naught, this is electric field and contribute to the dielectric constant. So three cases are equal to and less than and greater than phases. Okay. Maximum loss and weakness, there is a no dielectric present. In case of ionic polarization, similar fashion will be there. I dielectric constant and no ionic polarization observes. Okay. So all this behavior can be explained from this graph. This graph, okay. From this graph, okay. So this is a main factor. So if on the basis of this concept, uh, we can now answer that the ionic and the dipolar polarizabilities are derived considering uh, charged dipoles act like a rigid body. No, is not correct. We do not consider a charged dipole as a rigid body. Next is charged dipoles act like a simple harmonic oscillator. This is correct. We always uh, consider this charged dipole as a simple harmonic oscillator. Charged dipole resonant with a electric field at a certain frequency. Okay, this option also is correct. So this is the resonant frequency. This is the resonant region. Resonance frequency region. This region. Okay. So they actually vibrate at a specific region. Okay. This region. This specific region. So this option is also correct. That charged dipoles resonate with electric field at a certain frequency. At a certain frequency. Okay. And charged dipoles are free to move irrespective of the field. No, there must be some restriction. They are not free to move. There must be a restriction. What type of accident? There must be damping force. Okay. It depends on the frequency also. There must be a restraining force due to the simple harmonic oscillator. So everything acts, every forces acts when dipole oscillates with respect to the electric field. So it's not only free to move. So only two options are correct. They are simple harmonic oscillator and resonance frequency will be there. Now we can move to the question number 5. It tells about in a real dielectric, not ideal. We have already learned much about the real ideal dielectric, but this is not for the case of real dielectric. The question based on the real dielectric. Okay. The conductance G value. This is a very important value. G value. You already have learned that G, which is nothing but 1 by R resistance, not 1 by rho. Rho is different. Rho is resistivity, and this is resistance. Okay. This is resistance and resistivity. This is resistivity. This is resistance. Okay. So they both are different. Okay. So G actually depends on resistance only. So the conductance corresponds to the frequency dependence part of a loss current can be expressed as, okay. So you have to see the variation of conduction with omega, frequency of omega, how it varies with frequency conductance in a real dielectric or a real dielectric, where C naught is the capacitance, a relative permittivity, omega is the frequency. Okay, let's see for the case of a real dielectric. You are much familiar with this figure where uh, the variation of the phase dependency of current and the corresponding voltage and the corresponding currents are shown. This is the phasor diagram. This diagram is called the phasor diagram. In case of ideal dielectric, you can see in the ideal dielectric, if we plot the voltage here, the variation of ideal dielectric will be just like this. They are 90-degree I charging leads 90-degree to voltage. Okay, voltage grid. So ideal dielectric cases, voltage is current is led by 90-degree. This is 90-degree. But for this is for ideal cases. But in general, means in real cases, I do not follow 90-degree phase with V. There must be some loss in current due to the impurities like vacancies, interface, um, electrode material interface. Okay. Some defects present, there may be some defects due to all these factors. In real dielectrics, always exists some there always exists some loss. Okay, loss factor always exists. So this loss is also there, and the current, so there will be a net current that is called I total for a real dielectric after the loss factor is considered. So this I dielectric, if we take the projection of I dielectric, if we take the delta value with charging current, the one projection should be there in this direction, and the another projection should be there in this direction, loss direction. Okay, so charging direction and loss direction. This is loss, and this is charging direction. I charging, I loss. And the resultant direction is this. Okay. So there must be a loss in a real dielectric. So from this triangle, we can also find tan delta, which is equal to what? I loss divided by I charging. I loss divided by I charge. Okay. So this tan delta is called the loss factor. Loss factor. This tan delta is called the loss factor. Now, okay, here some important points I have highlighted that long range migration of charges due to ohmic conduction and its frequency independent, DC in nature. Ohmic conduction is frequency independent, but dissipation is due to dipolar rotation or oscillation. There is always a certain initial movement that is time dependent. So dipolar orientation always time dependent, not frequency dependent. And that's why two terms, one is AC term, which is dependent on omega. You already have learned much about this. I am just recapping everything so that you can just answer. So total current is nothing but charging current and loss current. Charging current is I omega c into V, and loss current, which is due to the frequency and DC. So these two terms will also occur. Now, what will happen in a real dielectric? When omega is zero for static DC case, so I total equal to I loss, GDCV. So mainly GDCV is mainly for omega equal to 0. This is 1 by R, I already told you. So epsilon is mainly complex quantity. We can uh, split it in a real and imaginary part. So the complex quantity of this is the dielectric constant in a medium, and this is the dielectric constant. Okay, this is nothing but a ratio of epsilon by epsilon naught, that is also V. So actually C value is K star C naught. Okay, dielectric constant into C naught value, where Q value is K C naught. So charging current is nothing but total minus loss current, dq dt. So dq dt is this, and V is nothing but V naught cos omega t. So here K star value is, and this. the overall conduction. So dc plus g omega c. Mainly g omega c occurs from this. This is dc. So g omega c value mainly omega k double dash c naught mainly exists. Okay. AC conductance value. So using this formula, we can now see I loss by IC ratio gives this value dc plus omega k double dash. So you can see that this k double dash value mainly gives you the loss factor. This total form, this total gives you mainly the loss. Okay. So that is why this is mainly shown here. This is the loss factor and this is the charging factor, with charging factor mainly depends on the real power of dielectric constant, and a loss factor mainly responsible for the imaginary part of dielectric constant. Okay, so if we consider actually DC part is very in real very low with comparison to the omega k double dash sigma. So we can just cancel it out, and if we cancel it out, only k double dash by k prime uh, exists. So tan delta is also the ratio between the imaginary part to the real part of dielectric constant. Okay. Here are different materials and their dielectric constant and their corresponding loss. Loss is nothing but the ratio between these two. Has been shown that aluminium shows low loss. Silicon dioxide also shows very low loss, but very low dielectric constant also. Barium titanate show, barium PVC show very large loss, very large dielectric constant due to defects and any other reasons. So, okay. Uh, so what will be the answer? Answer will be, uh, it can be conductance in a frequency dependent. So it can be omega. This is dependent on the pitch, the imaginary part of the dielectric constant. Imaginary part of dielectric constant. So it is the correct answer. It is not dependent on the real part. It is not dependent on real part. It is not, I should not be there. So only B option is correct. Question number 6. Okay. In the case of real dielectric, the permittivity exists in a complex form. Voltage leads the current. I just read the questions. Uh, I have already discussed, and then it is a uh, similar question and from the previous one, and loss factor and how charging current and how total currents are responsible in a real dielectric. Based on this concept, can easily answer the question. Okay, so I'm just checking. Everything is fine. Okay, so if anyone has any question, you can ask in the message section. Okay. So just read the question number 6. Okay. Let's see that in case of a real dielectric, not ideal. Okay. You are familiar with this. I total equal to I charging I loss. Okay. So uh, two projections are there in where I law and I charging. Mm, Two projection of I total has been shown here. Variation of current with voltage. Okay, you already have learned with this AC conductivity, it depends on K double prime epsilon naught plus sigma dc and omega epsilon naught K from as this terms goes out, sigma dc is very small. Sigma dc is very small with K double prime epsilon naught. So these terms goes to zero and only this term actually uh, K star epsilon r equal to epsilon by epsilon naught and also tan delta we know tan delta equal to K double prime by K dash. So K double prime equal to K dash tan delta. Just put it and in the place of K prime, it will gives us this value. So what will be the average loss? Just 1 by t integration of 0 by 0 t ddt v square cos theta due to v v naught cos theta cos omega t, and this loss also considers v naught. So 2 v naught comes. So 2 v naught not only one v and v naught. Okay, v and v naught. So only gives you v naught cos theta, cos omega t. Okay, and if we consider this, then we find the average power loss in a dielectric per unit volume. It is the dissipation power density per unit volume. It gives this value. So DCAC equal to 1 by R at a DC field. So actually, this is the main power loss term. Power loss term, which uh, depends on which term. It depends on tan delta loss factor. It depends on omega. It depends on E. It is voltage. Okay. So these are the factors for average power density in a dielectric. Okay. And the average power density in a standard equation for I square R by just using 1 by R GDC, you will find on this equation. Okay. So you can now answer the question that in the case of real dielectric, permittivity exists in a complex form K star I k k minus I k double prime k prime epsilon is also considered epsilon double prime sorry epsilon prime minus I epsilon double prime. So these are complex form in a real case. Okay, this is correct answer. The voltage do not leads, current leads. So this is incorrect. Current leads by the voltage by 90 degree minus delta. This angle is delta. So the total angle is 90 degree minus delta. From I total to I voltage. Okay. So current leads by the voltage by 90 degree minus delta. There is a power loss which varies between tan delta omega epsilon naught square. Okay, this time I have already discussed about it. Power density depends on omega epsilon naught k dash tan delta epsilon naught. So these are the main important terms. So there is a power loss also. Okay, so three options are correct in a real dielectric in this question. Okay, we can now move to the next question, question number 7. That it is telling loss tangent is expressed as this is just the you can just answer this question with the help of the previous concept of the question. Loss tangent is expressed as the loss of current to the charging current. Okay, we have already seen that from this diagram. Okay, that's loss tangent is nothing but loss current to the conduction current, charging current. And loss tangent is also dependent on frequency with GDC and omega k double prime C naught. And from here, when GDC is much less than omega k double prime C naught, okay, then we can find this relation, that is tan delta is equal to k double prime by k prime. So first option is correct. Ratio of loss current to the charging current. Loss current to the charging current. This is correct option. Okay. Ratio of imaginary dielectric constant to the real dielectric constant. This is the dielectric permittivity, which is nothing but dielectric constant. So imaginary dielectric constant and real dielectric constant, ratio between them represents tan delta also. So option B also correct. Ratio of capacitance to real material to vacuum, no, it does not depend on capacitance. So it only depends on dielectric constant. Okay. Real to vacuum, no, this is also incorrect. Imaginary part should be there. Uh, Ratio of imaginary impedance to real impedance, this is also correct. And this is very important point that you should know about impedance. For this, you have to understand the impedance spectroscopy. In any dielectric material, we represent the impedance value. Impedance is a complex term, and the complex impedance term, this is the complex impedance term. This complex impedance terms is Z prime minus plus IZ double prime, means a real impedance and imaginary impedance. Okay, it consists of real and imaginary impedance. And how it varies, you already have learned about this, in which where you can see that the loss factor is also there in a real dielectric. Okay, in a real dielectric, loss factor should be there. And we just represent tan delta is nothing but the imaginary impedance to the real impedance, as well as that is okay, loss current to the, as well as it is loss current to the charging current. Okay, so these are the loss factor and its corresponding representation. So ratio of the imaginary impedance, I just giving brief discussion of this is called the Cole plot, plotted between epsilon r double dash and epsilon r. This is imaginary part of dielectric constant, that is real part of dielectric constant. We have plotted it, and we can see that Cole plot is telling uh, uh, this is the this is for perfect dielectric case. This is for perfect dielectric case. Okay, the variation of epsilon r and this consists of a perfect circle, semicircle. This consists of a perfect semicircle for a perfect dielectric. Okay, and this is a point where it had been concluded that omega t value equal to t is the time, relaxation time, increasing frequency. Hmm. And for real dielectric, this is the case. You can see there they do not show the perfect semicircle. There must be some loss at low frequency. Okay, this is the low frequency region. This is the this is the high frequency region, low frequency region. You can see it, uh, some loss, and at the peak position where no variation of dielectric permittivity is zero. Okay, so at this position, omega t value equal to 1. Okay, arrows show increasing frequency. So omega arrow, this, so here high frequency is there. This region is called the high frequency region, and this region is called the low frequency region. Means in this region, electronic polarization, ionic polarization occurs, and with the increment of dielectric dipole polarization occurs. And in these cases, mainly the loss factor comes. Okay, in a real dielectric. But in a perfect dielectric, it completes the full semicircle. Okay. Uh, so actually, this arrow, green arrow, blue arrow is showing about the complex quantity, complex dielectric constant. This is nothing, this is just a general expression. This is the resultant vector where it consists the imaginary part as well as real part as well as the imaginary part. Okay, so everything is discussed very briefly in this figure, and this is the impedance spectroscopy where it is nothing but, and you can see for real dielectric, that is low frequency. This is high frequency, and this is low frequency. Okay. So everything you have learned in lecture series, and I are just recapping all those things. So ratio of imaginary impedance to the real impedance should also be there for loss tangent. Okay. Now question number 8. Okay. This question is also based on the dielectric loss. The power losses in a dielectric increase. Power loss, when the power loss increases in a dielectric material. So you have to know the power loss equation. What is the power loss equation? I have already shown you in the previous previous one to question, that how average power loss can be calculated uh, by considering the imaginary and the real parts of dielectric constant and their GDC value, GAC value. Okay, G is nothing but okay, this is the conduction value. So everything we consider, and finally we uh, average power consider. We comes to the this point. You can see it depends with tan delta and average voltage. So power loss in the dielectric increase when? How? When the power loss increases? It depends on when tan delta increases, when voltage increases. If voltage increases, it increases with square value. Means voltage increment factor is very important. So loss tangent means tan delta. Okay. Tan delta increment gives power loss increment. This is correct. Dielectric constant increase. No, dielectric constant actually. Dielectric. This is there must be a confusion. There you may confuse that this is not the dielectric constant actually. This is the real part. So actually dielectric constant. This is we cannot call it dielectric constant. Okay. Actually it depends on C value also, real part value. So capacitance value. So dielectric constant do not increase here. Okay. So this is not true. Resistivity, no, resistivity part is not in a power calculation. Average power, you cannot consider that resistivity for average power losses. Voltage increment, we can see that voltage increment. So voltage should increase in a power loss. Question number 9. It tells about the loss tangent of a material increases. Here, the previous questions told us about the uh, power increment, average power increment. It is telling about the loss tangent increment. Okay. So loss tangent is nothing but I loss divided by I charging. Okay. We have already learned about loss tangent. Loss means increment of conductivity. Okay. So when property of a material, dielectric property is decreased or degraded, we term this as a loss in a dielectric material. So we can see this expression sigma AC. We have already uh, learned about that. The omega epsilon k dash, that is k dash tan delta. This is omega epsilon k double prime also. Okay, we have actually first GAC. Okay, this is the term. Okay, this is nothing but the conductivity term. It depends on tan delta. When we tan delta can be expressed also imaginary part by real part. Okay, from there, from this value, tan delta comes. Okay, so conductivity should be increased for loss tangent increment. Okay, so option D is correct. But what is the dependency of temperature? Temperature actually increases the conductivity of a dielectric material. Okay. It first of all, when we apply temperature in any material, it creates vibration of atom at its equilibrium position. After increment of the temperature, it actually goes from valence shell to conduction band electrons, so that a conduction of current is generated. Okay, due to the conduction of electron. So due to the conduction of electron, it takes electrons of atoms takes energy from this temperature, and it goes to valence and conduction band, and valence band to conduction band. Okay, after taking thermal energy. Okay, so this also also be a factor. This will also be a factor that temperature increment occurs loss tangent increment. Grain size decrement, no, grain size decrement do not creates loss tangent. Grain size increment creates, but when grain size is decreased, means means local field, local random field is created. Local random field is created. That's why entropy is increased. Entropy S is increased. That's why G is increased. G is increased. Oh, sorry, G is decreased. G decreases. We need this G decrement. Means total free energy decrement means when we get the total gives free energy decrement, we can tell that the system is in equilibrium state or a static state. And we always want, or every system or every material system, every universal system wants to get its stability or static system. That's why G should be decreased. And grain side is a very important factor for this. Okay. You can see that temperature increment, how temperature increment depends on tan delta AC. The loss factor, when temperature is increased, tan delta is increases. Okay, temperature increment increases tan delta. Uh, this is LL Hinch. I have collected this from LL Hinch. Okay. It shows the variation of tan delta with frequency at certain frequency. This is there's a loss, higher loss frequency, dipolar frequency, and it also increases with temperature. This is omega naught 1, this is omega naught 2, omega naught 3. Okay. Three peaks have been shown. You can see at 24 degree omega naught. Okay. Okay, so this is all about thermal breakdown. What do you mean by thermal breakdown? Heat dissipation in a sample due to current flowing through the defective parts. Okay, it is ionic defects in plates. That's why I am telling that the when a material consists of defects, vacancies, uh, some external factors such as electric field or temperature means when some energy is we are going to give this material, then first of all, defects and vacancies reacts with this, and they have more probability uh, to be conducted when this after getting these external forces. So these are the very important factor of temperature. Uh, Temperature rises these factors of defects and vacancies, and this increases the defect concentration. That's why leading to increase the conductivity in the material. Leading to increase the conductivity. That's why loss is also increase. That's why loss is also increase. Tan delta therefore is proportional to the temperature. Okay. So option defect density increment is also true. Defect density increment causes uh, defect density causes the conductivity. Okay, defect density causes the conductivity. Okay, next we are going to the question number 10. It is telling about that a pole-pole plot, pole-pole plot, it is nothing but minus z double prime versus z double dash plot, which is impedance spectroscopy plot. Spectroscopy means impedance is z prime, z double prime. They are called impedance, but spectroscopy. Why do we call spectroscopy? Spectroscopy means these two terms, z double prime, is nothing but the function of frequency. Okay. So when we plot z double prime versus z prime, we consider the frequency omega or f. Okay, tau. So this is the frequency spectroscopy. At different frequency, we are taking the values of um, z prime at z double prime, impedance value. At different frequency, we are taking the value of impedance, so that we are telling this as an impedance frequency spectroscopy. You can also tell it. Okay. Okay. So this is the circuit representation of a dielectric and the impedance analysis. We can see two parallel capacitance and a corresponding resistance is also there. This is a circuit representation of impedance analysis. Okay, just you have learned also. I am just recapping all those things so that you can answer the question that, okay, okay. Data analysis after dielectric characterization often requires modeling of dielectrics. You can, after data analysis means you are getting the dielectric value, dielectric constant value, its corresponding imaginary value, real value, and their corresponding frequency spectrum value, and their corresponding temperature value, Curie temperature value. Okay, everything you can get. But how do you represent them? How do you model them? So characterization is different. First, modeling of dielectric, but how um, capacitors, what type of capacitance is there, how they are arranged. Okay, everything depends on uh, everything we can explain with the impedance spectroscopy graph. So that is the representation importance of impedance spectroscopy. We can represent in a circuital way of grains or grain boundaries and their contribution of in dielectrics. Contribution is in conductivity. From here, you can calculate the Arrhenius law and the conductivity portion. We have to show actually mainly the low conductivity. In case of dielectric material, means low loss. For to get a perfect defect free, you cannot get free, but less defect less dielectric. So tan delta should be very, very less. Conductivity should be very, very less. Very less. Okay. So these are the properties of a dielectric, perfect dielectric. So that we can get a higher dielectric constant. We can get a compact structure in a dielectric material. Okay. So for this, we must have to know the circuit representation and its how they are connected and how they are conducting current and other things. Okay. Modeling of dielectrics. It is called the modeling of dielectrics. So it is the equivalent circuit. A perfect dielectric material can be modeled by equivalent RC circuit, equivalent RC parallel circuit that is shown below. So this is the model of a dielectric. So how do you calculate the impedance? One is admittance and another is impedance. Admittance can be calculated by the reverse equation. They are related with reciprocal. Related with reciprocal. Okay. That is admittance, that is impedance. There is two impedance circuit, that is Z1 that gives Z2. Okay, so Z1 is 1 by omega C1, or here resistance is also there along with capacitance. Okay, so these two terms we have to calculate, and finally we get admittance as a this. So what will be the time constant here for R2C2? As T2 equal to RC, time constant is nothing but RC. If we see in a simple um, LRC circuit, you can see that only when L is 0, then you can see the time constant of a LRC circuit is RC. Okay. So for this case, T2 will be up to C2, then admittance can be represented as just replace T2 value with R2C2 value. R2C2 value. So R2 we can represent C2 by T, and C2 we represent 1 by omega C2. Okay, just represent C2. Just represent R2 in terms of C2. You will get that. So C1 is there, C2 is there. This is a function of C1 and C2. Okay. Now 1 by Z, y equal to 1 by Z, we can see that this is a real term and this is a imaginary term. Where so this is termed as a epsilon double dash, means imaginary part of dielectric constant and real part of dielectric constant. Okay. and omega C naught by epsilon naught as a constant. So this gives a dielectric permittivity value after substituting this epsilon naught value at these positions. So you can get the dielectric permittivity value of real and imaginary permittivity value. Okay, so this is infinity. This is infinity. So C2 is nothing but saturation minus infinity. This is the dipolar polarization mainly. This term arises from dipolar polarization. Okay, C1 is mainly the saturation infinity. Sorry, saturation. It is dependent on lower frequency. Okay. Lower frequency. Okay, sorry, higher frequency. Higher frequency. Higher frequency gives you C1 value, and there epsilon saturation minus epsilon infinity into C naught value gives us the C2 value. Okay. So by so through this concept of C naught value and C2 value, Cole at 1941 plotted at a frequency response as a spectroscopy. Okay, spectroscopical description, 1941. Electrical response of dielectric material by plotting epsilon double prime and epsilon prime. And he just gave this type of Debye equation. So if we plot these two in a complex plane, we get a semicircle for a real for a ideal dielectric. This is not a real dielectric. For a perfect semicircle, we will get for a ideal dielectric. Okay. So what impedance spectroscopy is? What is the impedance spectroscopy now? The frequency response of impedance of above circuit will also yield a semicircle in the this Cole actually plotted the dielectric constant value. Okay. And what is the impedance value? The corresponding impedance value means Z double prime and Z prime value. If we plot the corresponding impedance value also, it also yields a semicircle in the complex plane between real and imaginary parts of dielectric ones. Such a response represents a capacitor with losses. Such technique of characterizing dielectrics is called the impedance spectroscopy. Okay. Frequency responses of impedances. That's why I have taken frequency response of dielectrics. The intercepts of semicircle on the x-axis represents high and low frequency dielectric constant. Okay, this is very important point. Epsilon r infinity, that is epsilon r infinity, and epsilon r saturation dash, that is high frequency. This is the frequency representation. This is the low frequency where dipoles acts, and here electronics and ionic polarization acts. So this represents sets E dash, R infinity, E R infinity, and E R saturation. This is just the representation of polarization at different frequencies. Okay. And you already know about this. By using this is the representation of semicircle. X square plus y square equal to c square. Just value, taking the value, we can just express the epsilon r dash value in a Cole plot. Okay, the perfect dielectric shows the perfect semicircle, and the real dielectric shows high losses. Okay, so all these are the concepts you already have learned about in these lectures, in the previous lectures in grade 5. And so what will be the answer of question 10 is a Cole plot is semicircular in nature for an ideal dielectric this is true, a Cole-Coulomb plot is a plot between imaginary part versus real part of a dielectric constant. This is also true. And this is obtained at static field measurement. This is not true. This is not measured at a static field. This is measured at a alternating current field, AC field, not DC field. Okay. This is always measured. That's why real and imaginary part of dielectric constants occurs. Okay. Not in static field. Or is circular in nature for a dielectric? No, it is not circular in nature. So only two options are correct. A plot between imaginary part and real part of dielectric constant and semicircular nature in a. Okay. So we can now move forward to the question number 11. It's a problem. But the problem is the impedance value of a parallel RC circuit, parallel RC element. So you have to know what the parallel RC element is, where R is the resistor or C is the capacitor value. You have to find the impedance value. So this is the circuit where a resistance R and a capacitance R connected parallelly in a system. Okay, connected parallelly in a system, you have to find the impedance value. Impedance value. So this is the admittance 1 by Z. What it gives? It gives the value of resistance 1 by R. For resistance, the impedance value, it's only resistance value. And when we consider the capacitance, impedance value of the capacitor is 1 by j omega c. Okay. Impedance value of a capacitor is nothing but 1 by j omega c. So this value, if you consider this value, then what z that means the impedance of a system of this system occurs like this 1 by 1 by, and R will be goes up from the uh, numerator term, and in the denominator term 1 plus omega j square c square R square will be there. Okay. This is nothing but the modulus value of, from here we can see that R by R plus j omega RC. Okay. Okay. So what will be the value? Sorry, this will be only 1 plus j omega RC. So this is a constant imaginary complex term. Complex term. Okay. And what will be the modulus value of this term? Modulus value this term is mod of 1 plus j omega CR gives you root over of this term plus j omega CR term. Okay. It comes out to be, it comes out to be 1 minus j omega CR. J should not be there. Omega square, c square, r square. And that's why, and this should be positive because omega square, sorry, I square, I square gives you minus 1 value, and this minus 1 turns out to be plus 1. Okay, so at last we get this term. Okay, now you can easily answer the question. If you add up these two terms, you can get that the answer is R. This is R by 1 plus omega square r square c square, and minus this term. This is the real part, and the I omega r square c by omega square r square c square plus 1. So this is real part and this is imaginary part. Okay. So this term consists two parts. One is real part of impedance and another is imaginary part of impedance, and this will be the correct answer. Question number 11, B. Okay, this is just a simple calculation. Okay, so we can now move forward to the next question, question number 12. It is telling about that in the Cole-Cole plot, this is the Cole-Cole plot. Okay, this is the Cole-Cole plot. Higher frequency, this is the higher frequency region. It is telling that. So this is the higher frequency region, IF region. Higher frequency intersects on E dash R. So this is the real, this is the real axis. So in real axis, where the where this curve, this impedance spectroscopy curve cut at 2 point, at a higher frequency point, at a lower frequency point. So how do we term this? We term higher frequency part as a epsilon r dash infinity, and the lower frequency term as saturation, epsilon r dash s. Okay, so that is the interpretation of mm, the impedance spectroscopy uh, in a two-dimensional figure and its corresponding value of lower frequency and higher frequency values. So in the Cole-Cole plot, higher frequency intercepts on epsilon r dash axis corresponds to what? What will be the answer? Infinity. Higher frequency at higher frequency means what? Higher frequency means what? Higher, what higher gives? Electronic polarization, ionic polarization. We have seen that polarization versus time plot gives these types of behavior. Okay, this region tells us about the electronic and ionic polarization region at a very short time. Very short time means at a very high frequency. T less means frequency very high. Okay, much high. Okay, and this is the PS saturation region in which time is very high. Time is very high. That's why frequency is very low. So this is low frequency region. So that is uh, termed as a S. That is termed as saturation region. In saturation region, how dielectric constant behaviors? This is termed in uh, impedance spectroscopy also. Okay. So based on this concept, you can answer that at a higher frequency region, this is this. No, this should not be correct. So only B option is correct. Okay, now we can move to the next question, question number 13. The difference between static dielectric constant, that is the static dielectric constant, and high frequency dielectric constant corresponds to what? This is the dipolar polarization. You already have learned about dipolar relaxation or Debye relaxation. This is just the summation representations of dipolar Debye relaxation. You already have learned it. Although I briefly discussed, I have taken some capture for you that this is static dipolar at a very low frequency, sorry, high frequency. At a very high frequency, this is the uh, dielectric constant, real dielectric constant, there must be a difference at a certain point, 1 log omega t value equal to 1. At this certain point, there must be some loss. This is the loss factor of imaginary part of the dielectric constant. We already have learned that. And there is a difference. This is the relaxation. And this difference, epsilon r for static and epsilon r for infinity. This term is nothing but the dielectric relaxation. Dielectric relaxation term. Dielectric relaxation term. Okay. From here, dielectric relaxation term has been offered. It is everything. Relaxation is mainly dependent on the frequency and how this frequency creates this relaxation. You already have learned about. But PS, what is PS? PS is nothing but the difference between this. Okay. So epsilon RS is a static dielectric constant, a dielectric constant at a very low frequency. Or epsilon at infinity is a dielectric constant at higher frequency, very high frequency. Covering electronic ionic polarization, as I have already told you, this kind makes sense because dipolar polarization, this is the dipolar polarization, very, very important, occurs between these two ends of the frequency. Bipolar polarization always occurs between middle range, at a higher frequency range, not at a higher frequency range, not at a lower frequency range. It occurs at a very this position where dipoles get relaxed, dipolar relaxation, and this frequency region is called the dipolar relaxation region. Okay, so based on this concept, you can now answer the question number 30. It tells about the difference between static dielectric constant epsilon dash Rs and the high frequency dielectric constant epsilon R infinity. This corresponds to what? Total polarization, no. Difference total polarization do not tell. So this is not correct. Not only ionic polarization only tells about the higher frequency range. Okay, this. So ionic polarization is not also true. Electronic polarization also tells about the higher frequency range. Only dipolar polarization exists between these two ranges. Okay, so dipolar polarization will be the answer. Next, question number 14. Okay, it's already 7:45, only 15 minutes left. If still you have any question, you can answer. So you can ask me. You can ask me in the message section. If you have any question of the 13 questions, I have solved it, and only 2 questions are left. 15 minutes are also left there. So okay, let's see the question number 14. It's a numerical problem about a parallel plate capacitor. Okay, let's see what has been given here. Okay, let's consider a capacitor with a dielectric permittivity has been given. Okay, this is nothing but C by C1. Capacitance at medium or at free space capacitance. Free space capacitance, you already know it. Okay. And effective surface area, two parallel plate capacitor, if we consider two parallel plate capacitor is connected to a battery in a charging position, and area is given, and there should be a distance between them, thickness, and a dielectric material is inserted inside this. This is the dielectric material. Okay. So now, and having a capacitance of 6 microfarad, which is this? This is this capacitance value. What will be the field strength? Field strength means what will be the E value? Okay. E value, if the applied voltage is 15 volt, E value actually, strength is nothing but voltage applied per unit distance. So you must have to find this distance value you must have to find T value. Okay. So you know epsilon value, surface area is given, capacitance is given. You must have to find out the D value. Applied voltage is also given. Just find out the D value. You already know this famous equation C equal to epsilon A by D for a parallel plate capacitor. Just find out the 1 by D value. It is nothing but C epsilon A by C is nothing but C by epsilon is nothing but epsilon. I have epsilon R is epsilon by epsilon naught. So what will be the value of epsilon? Just multiply this and we will get the value of 1 by T. C is known, epsilon naught is known, epsilon R is given, A is given. Just put all those values, 15 into C value is put it, epsilon naught value is epsilon naught, and so field strength will be voltage per unit length, will be the field strength. Okay, so and this is the epsilon value, this is the epsilon R value, and this is the area value. I have put it all those value. You can see, just calculate and you can get it in a, this is 10 to the power 6. Okay, this is 10 to the power 6. So it is in a megavolt. Okay, so 35 megavolt per meter. This is the field strength of this parallel plate capacitor. Okay, so 35 megavolt per meter will be the field strength. Okay, this is just a. Okay, so last question, question number 15 is upon increasing the temperature, what are possible observation in the frequency dependence of the dielectric? Okay, it is already have been and told in a lecture session that how dielectric constant loss value possible in the frequency dependence of the dielectric behavior. Tan delta is proportional to T. Also, epsilon r also increases with T. Okay, so these two value you must have to consider that you have already know about the relaxation equation. Okay, dp dt equal to 1 by tau P saturation minus P infinity. By using this equation, just at large T, just P equal to Ps. At small t means very high frequency, very small t means very high frequency. That P bipolar equal to 0. Just put this boundary condition. Okay, you can get this. So so you have already learned all about this. You have learned the graphical representation of Debye equation. Okay, just I am saying that. Okay, so figure 2.5. This figure you can see I have collected this figure. You can see that tan delta AC value is increasing from with the increment of temperature increases. T increases. Okay, tan delta value also increases. Along with this epsilon r value, also increases with the increment of temperature. This has been taken from this principle of electroceramics. This is the, and if we plot the frequency variation with temperature, we will get a straight line. And at different time, it had been taken. So time factor will also be there. Okay. So this is the higher temperature side. This is the lower temperature side. Sorry, This is the lower temperature side, low temperature, it's the high temperature, high temperature. So temperature increment, this frequency is also increased. Okay. So this is all the representations about, so now we can answer the question that upon increment the temperature, what possible observation in the frequency dependent dielectric variable? Dielectric constant increases, peak in the loss tangent shifts to the higher frequency range, shifts to the higher frequency range. So this is the plot of higher frequency. You can see that for higher frequency with the increment of temperature, with the increment of temperature, frequency is also increases. Okay. With the increment of temperature, frequency is also increases. So peak in the loss tangent shifts towards the higher frequency range. Okay, it is already 7:53. Only 5-6 minutes are left for to complete 2 hours. And if you have any question, you can ask me. Okay, so I am just checking that whether I have. If you have any question, please tell me. Any question, Anirudh? Just tell me. Okay, Anirudh. Okay, okay, let's checking. I'm checking, just checking whether I have done all the questions or not. I think you have learned, understand all the concepts and questions, and I have tried my best. Okay, question number 8 has been done, 9 has been done, 10 has been done, 11 has been done, okay, 12 has been done, 13 has been done, 14 has been done, 15 has been done. Okay, okay, everything I have completed. Okay, now no questions are there. So we can end this meeting today. See you next week. Okay, good night. Okay, you can leave now.